for our last lesson in Chapter 3. That's right, Chapter 3 has 10 sections on it. What? Anyway, related rates, that's what we're talking about. It is a major application of derivatives and, in particular, implicit differentiation. And our goals are two. We've got two, and we're going to split this lesson kind of right down the middle. The first part of it is going to be about learning to implicitly differentiate an equation with respect to time. Now, the equation itself doesn't have time in it as a variable. For example, we have, let's say, the Pythagorean theorem. And the Pythagorean theorem is relating the sides of a right triangle, and those sides could be changing with respect to time, even though t is not a variable that is in that equation at all. At least I don't think Pythagorean theorem has time in it. Maybe I've been doing it wrong all along. Anyway, after we get some experience with implicitly differentiating with respect to time, we're going to apply that to solve some real world or real life related rate problems. And those are the kinds that you will see on the AP exam, either in the multiple choice section or in, very frequently, the free response questions. Okay, so let's take a look. So speaking of that, this is taken from a free response question from the AP Calculus exam. Insert year here. I don't remember what it was, but it said oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. The oil slick takes the form, of course, of a right circular cylinder with both of its radius and height changing with time. Okay. At the instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeter, the radius is increasing at a rate of 2.5 centimeters per minute. At this instant, what is the rate of change of the height of the oil slick with respect to time in centimeters per minute? Whew! All right, so that's a lot to process. And when you see a question like this, I don't want you to get intimidated, especially right now, because we're going to break this up into small little chunks. By the end of it, you see a problem like this, it's one of the easiest things that we'll do on that calculus exam. All right, which brings us to our first objective, being able to implicitly differentiate an equation with respect to time. So the picture here, you can see that there's a collection of photographs. First day of school, it looks like, for this kid. I don't know when he went to kindergarten. Whoa, where are you going? I don't know where it looks like he went to kindergarten in the 1940s, and then all of a sudden color came into play. What happened in year 4? Maybe his shorts were dirty or something. They were still in the hamper. They're all wrinkly. And then back here on the 9th grade, as soon as he entered high school, look, he really liked that shirt. He wore it two years in a row. You know how it is. First day of school, you've got your outfit for the first day of school picked out like a week in advance. Like, he planned that. It wasn't just like, oh, it was right there on the end of the bed or right there on the floor. Here, I guess I'll just wear that. No, he planned it. Okay, anyway, so when we come back, we're going to start this process of implicitly differentiating with respect to time. Before we even do that, though, we're going to start translating some words into some notation.